Hello students, let us continue with Unit 5 of Communication Theory 19EC 403. Let us quickly recollect course outcome 5 for 5th unit, which is to verify sampling and quantization technique, with the concept of which we will be able to implement few pulse modulation techniques. So in your previous session, we might have discussed about the concept of sampling, Nyquist rate, as well as the necessity of quantization, what are the various quantization methods available, as well as quantization error, and we of course defined what is quantization noise. So in today's topic of discussion, we will move on to the digital pulse modulation technique, pulse code modulation. So whenever we talk about pulse modulation, we do have analog type, where we learn about pulse amplitude modulation, pulse width modulation, and pulse position modulation. When it comes to digital kind, we focus more on pulse code modulation, and this is the most preferred method of digital modulation, of course. Can you just look at the block diagram shown in here in the slide? So this shows the basic building block of a digital communication system. So the first block is the source, and then you have a source encoder, and then comes the channel encoder, and here comes the role of modulation. So this is a modulator, after which you have a demodulator, where we try to recover back our signal, and then comes the channel decoder, source decoder, and finally the user end. So we have of course a medium between the modulator or the transmitter end and the receiver end, where you have a demodulator, and we normally call this medium as a channel. So let us quickly run through the function of this communication system, digital communication system block. So as you talk about the digital communication block, we went through encoder as well as a modulator. Am I right? So this encoder actually helps us to code our bits. So here comes the role of digitization. So we try to assign a code or a binary value for every sample of our analog component. Okay, so we define several line coding techniques, and we try to process our encoding mechanism before modulation. So as digital modulation comes into picture, we try to focus now about pulse code modulation here. So what is this pulse code modulation? So in case of pulse code modulation, here a particular signal or the analog signal is pulse code modulated, or we try to convert its analog information into a binary output, or we try to convert the analog input into a binary sequence, where we represent them as ones and zeros. So the output of a pulse code modulation will resemble a binary sequence only. So you can observe the waveform shown here in this slide. So the first one represents an analog, and the second one is the pulse code modulated output. So this is how we try to represent. So instead of a pulse train, the pulse code modulated output produces a series of numbers, where you have binary values, either 0 or 1. Okay, series of numbers or digits, and hence this process is known as a digitization or a digital. So here each one of these digits, though in binary code, it represents the approximate amplitude of the message signal. Clear? So however, I try to encode it as a binary value. Every code or every binary value represents approximately the amplitude of the input signal or the modulating signal. Okay. So in case of pulse code modulation, the message signal is represented by a sequence of coded pulses. So the message signal will be achieved by representing the signal in discrete form, both in time as well as in amplitude. So this is the basic concept behind pulse code modulation. Yes, so here comes the block diagram, where we try to generate as well as receive a pulse code modulation output signal. So the first half is the transmitter section, this region, where we have analog input signal, and then you have a low pass filter, a sampler, a quantizer, and then encoder. So after that, you have the receiver section where you have a regeneration circuit, decoders, reconstruction filter, and then finally our user end. And in the channel, we'll be able to observe two blocks which are known as regenerative repeaters, and this is mainly like an amplification. So this is just for boosting up our signal, okay, both in the path of transmission as well as in the path of reception. So the basic operation in the receiver section will be regeneration of impaired signals, decoding and reconstruction. Keep that in mind, okay? So in case of transmission, we mainly focus upon sampling, quantization and then encoding. So now, what is the role of this LPF or low pass filter at the transmitter section? Yes, so this low pass filter helps us to remove all high frequency components, whatever is present in your analog input signal. Okay, so this greatly helps us to avoid your aliasing effect. We might have discussed the concept of aliasing during sampling theorem, right? So when we defined the sampling Nyquist theorem or Nyquist rate, we came across an interference, unwanted interference called aliasing mechanism, right? So in order to remove or avoid this aliasing phenomenon, we deploy a low pass filter which is helping us to remove the high frequency components present in the analog signal, whichever is greater than the highest frequency component of the message signal. Okay, so then comes the role of a sampler and quantizer. Hope we need not once again recollect it. So we'll quickly move on. Yes, so the next block is the encoder. So as we discussed earlier, this encoder assigns code words to quantized sampled values. So previously we might have defined the quantization levels. If suppose the quantization levels are 16, then we assign every sample with a 4-bit code word. Okay, so that is the main job of an encoder. And the next comes regenerative repeaters. So as it suggests, repeaters, they are mainly deployed at different locations along the channel to control the distortion and the noise levels. Okay, so we try to boost the signal during transmission. So the main the main operation or the main functionality of these regenerative repeaters are to equalize the received pulses, and you deploy few timing circuits which is greatly helping us to make a decision or to just to detect whether you have a signal pulse to be present or not. In case if it is not present, we'll try to generate a bit error and we transmit that erroneous bit to the receiver end. Okay, and then comes your receiver end where the first block is of decoder. So this decoder tries to reboot all the received bits. It makes it a complete words, collects all the words and then decodes them as a quantized PAM signals. So this tries to decode them as a quantized pulse amplitude modulated signal. So now the received or the quantized pulse amplitude modulated signal will be made to pass through a reconstruction filter, which is once again a low pass filter, so that the original analog signal can be reconstructed back. Okay, so this is how we represent the PCM waveform. So it receives the signal from the reconstructive filter output in its analog format. Okay, so as we talk about PCM, since this is a digital modulation, this definitely requires more and more amount of bandwidth than the original analog signal mechanism. So the bandwidth required to transmit this kind of PCM signals depends mainly on the type of line encoding techniques we deploy also. Okay, and these are some of the important relations which we need to keep in mind. So quantization noise, the other parameter is signal to noise ratio, and the bit rate and the bandwidth required for PCM signal. Yes, and then comes companding mechanism. So what is this companding mechanism in pulse code modulation? Companding, just observe the word companding. So when you split this, I can say it as compression followed by expansion. Yes, so I have a combination of these two processes, compressing and expanding, which means that I have a process where I go for both compressing of signal as well as expanding of signal. So my technique compresses the data at the transmitter of PCM and expands the same data at the receiver end of PCM. Okay, so why do I need to do this companding mechanism? That's a good question, right? So the effect of noise and crosstalk or the other unwanted interferences can be greatly reduced by implementing this companding mechanism. So you have a compressor, a uniform quantizer, and then an expander. So I'll be able to improve my signal to noise ratio. So this is the concept behind companding, which is a process of both compression as well as expansion. Under companding, once again, you have two more techniques. And the first one is A-law companding technique and the other one is mu law companding technique. So A-law companding technique is a linear mechanism where you will have a mid-rise at the origin and a non-zero value. Okay. So here I define the parameter a constant value A, which is equal to 1, and you will have a linear curve, and observe that the mid-rise, the quantization levels, right? We try to mark the quantization levels. So the mid-rise will be there at the origin, and this is mainly used in case of PCM telephone systems, whereas this mu law companding technique will be observed similar to mid-thread type, and this has a mid-thread at the origin and it will have a zero value. So I fix the parameter mu to be 0, where the characteristic curve will be linear once again and no compression is done here. Yes. So now we are moving on to one of the important parameter to analyze the performance of our PCM. So this is signal to noise ratio or signal to quantization noise ratio in PCM. So this is defined as the ratio between normalized signal power to the normalized noise power. So you can observe the equations from the given slide, and the discussions will be discussed in the forthcoming classes, and we'll try to solve problems in classes. Thank you.